Hey guys, this is Jay. I study BTech Computer Science at IIT Delhi. I started my internship at EduTech Learning Solutions Private Limited at the end of my first year. The duration of the internship was 6 weeks, during which I developed the ELSPL ML community repository on GitHub. This internship was a platform for learning the various concepts of machine learning and the maths behind it, and trying to build models on my own from scratch. I made various exercise Jupyter notebooks for this and committed them to repository. Along with that, I also listed all the resources which I referred to and were of great use to me for understanding the concepts and the math behind algorithms and so on. Thus, this repository contains my understanding of the various concepts of machine learning, and I hope it will be a very useful learning resource for students new to ML and a refreshment for those with previous experience. In this video, I shall give a tour of the ML community repository. So you go to GitHub and type ELSPL ML community, and this is the one I have been working on. The community page is divided into two parts. There's the docs, there's the labs. Docs have some good reference courses that will be really helpful. Uh, yeah, so there are some books, there are some online courses, and I would suggest that you go through these when you have time. They're really helpful for learning about the various concepts and the maths behind machine learning. On the other hand, labs are exercises and examples that are created to, explain a topic further. The labs also contain useful resources that will help you to understand the concepts and maths further. Yeah, the resources. So these resources have been distributed lab-wise. These are some great references from which even I learned ML while making this community, and I guess it will be very helpful for you. Before I explain the labs in detail, I would like to add that we love contributions, and we would like for all of you who are listening to this video to go through this community to learn something new and contribute to make it stronger, to make it further useful for students. So instead of going directly to pull request, please go to the issues and create a new issue, be it regarding enhancement, be it regarding some issue that you faced while using this community repository, and just make a new issue and we can discuss it over GitHub, and yeah, and then we can go further and implement that change. You can make a pull request and we'll merge it. And yeah, before contributing, just make sure to go through the code of conduct and the contributing document. Uh, it will help you as well as me to maintain uniformity of the repository. So let's talk about labs. I will be using nbviewer.jupyter.org to view the content of this labs, as this is a faster option. So the labs are divided from lab 0 to lab 5, and there's the resources section we talked about earlier. Lab 0 is basically getting started with Python, as this repository will have codes written in Python exclusively. So lab 0 is about Python basics. It's about important Python libraries like matplotlib and seaborn for visualization, numpy for working with arrays. There's pandas for data frame basics and working with data, and of course there is information about Git, since as a contributor you must know Git and GitHub basics and how you can contribute. So let's go into lab 0. So there's a quick readme about the purpose of the lab, the sequence which I think you should follow. There's this brief introduction about the exercises, and yeah, so for example, there's this baby python.ipynb. It gives a basic rundown of Python, the basic commands, the print and looping and decisions and indexing lists. Then there's dictionaries, there's strings, there's functions. Basically, this notebook will help you get started with Python. And yeah, if you know Python already, then yeah, feel free to skip through this. Similarly, there's this tutorial notebook on Git. Its basics and what you can do with it, like forking and cloning and branching and all that. There's one more very useful resource to learn Git. There's this https learngitbranching.js.org. It will provide a playful way with which you can learn Git, and yeah, this was a very good resource for me as a beginner, and I think you should go through it once. The actual machine learning starts from lab 1, where we have an introduction to linear and polynomial regression and the various maths required for it. There's gradient descent and normal equations, and the you should be familiar with the derivative, the partial derivative, what's convexity of a function. Yeah. And after regression we look at SVM classification. There's a support vector machine classification. So let's open lab 1. Let's look at regression first. So this is the regression notebook. Each of the notebooks will consist of some theory about what I understood when I first read about regression, and after that there's the code. There is first, as we see, some testing on toy data. The red points are actually sine curve and the blue points represent our data. That's after we have added some noise to it. Then we have included linear and polynomial regression into one function with this parameter m, which controls what it is. When m is 1, then it represents linear regression, otherwise it represents polynomial regression. For example, for m equal to 2, it will represent a quadratic regression. So first method of solving is by using the normal equation. Then we have this curve which we got. It's pretty accurate. Then there's a second method using gradient descent. There's again some theory on gradient descent, and then the algorithm. That's our error, and closer look at that. And this is the function that we get using gradient descent, which is quite similar to the one we got using the normal equation. And then we have some real data. This is taken from UCI repository, the auto mpg dataset. So yeah, this link can be found here. The data looks something like this. So we need to predict the miles per gallon of a particular car given its cylinders, displacement, its horsepower, weight, acceleration, etc. As you see, we have used pandas here to work with this data, removing some columns like model year and origin and the car name, and viewing the data, replacing the missing values, and converting data types, shuffling, splitting. So basically, to work with the data we use pandas, and hence you should be well aware of this library, and you should know how to use it. Then there's regularization, but that's content of lab 3. So in lab 3 there is a reference to this notebook again. So we have regularization, this L1, L2. In this notebook we have used L2 regularization with 3 values of lambda, 1, 1000 and 0, that's no regularization, are tests, and that's our losses. So then we also benchmark the model using sklearn. Now sklearn is a machine learning library which Python already provides for various machine learning functions like regression, classification, you know, ridge methods, and so on, decision trees, random forests. So, sklearn is a very good library, but I would suggest doing things from scratch as well to understand the underlying concepts, and use sklearn only to benchmark the models that you have created. So we have this benchmarking, some footnotes, and that's a notebook for regression. Similarly, the notebook for SVM, there is this SVM from scratch. This talks about a linear kernel with toy data. There's SVM polyscratch, which deals with a polynomial kernel, and this notebook deals with a polynomial kernel but with using sklearn. So again, there's this theory and the code. This is a toy data, and we will pass a hyperplane through this. This is a error graph. So the we have used the hinge loss function here. So the error decreased from 4, then 3, then 2, 1 to 0. And this is our line which our algorithm generated. Green points are some testing points which I had added just for fun. Then there is sklearn again. You use sklearn to generate the same line which we got using our scratch algorithm. Similarly, we are now using the SVM polynomial kernel, which will also allow us to classify data points like these. And we have some toy data here. Yeah, and we have separated this using a nonlinear boundary, and a process similar to that using sklearn. This is basically a continuation from the previous notebooks, and this also creates a figure similar to the one we just saw. Lab 2, I think, has the most intensive math of this entire course. So lab 2 will, you will look at some mathematical concepts like Jacobian, Hessian, Laplacian, the probability terms, types of probability. There's the Bayes rule, inferential statistics, priors and posteriors, Laplacian approximation, and we'll use all of that in logistic regression, as well as we'll also use Newton's method for logistic regression. So let's dive into lab 2. Lab 2, there are two notebooks. There's logistic regression and MAP, which stands for maximum a posteriori. So logistic regression consists of, again, the theory part, and then the code part. As you can see, we have used the maximum likelihood estimation, MLE, to find the likelihood and maximize it using Newton's method. And after that, we have found out an optimal value for this theta, for which the model will classify. So again, there's the code. We have two types of play data, one with linear separators and one with non-linear separators, or the circular data. There's the different functions for this, and this is the first type of our toy data, where we can find a line which separates the two data sets. And as you can see, the logistic regression produces such a line. This is the second type of our data, which is kind of a circular data, and we need a non-linear separator for this. And our algorithm can also produce a non-linear classifier. And when we implement this on real data, many of the times we get data which are multi-class. That means either you can have a result of 0, 1, 2, 3, and so on, instead of a binary data. So there are two methods for that. One is modifying our MLE, that's the maximum likelihood estimation method, for multi-class classification. The second one is one versus all method, where we take one class and to be 1 and all others to be 0, and we repeat that for the number of classes. We repeat that as many times as the number of classes. So that's method 1 here. There's method 2 as well, and as usual, using the sklearn, we benchmark our model. That's lab 2 for you practically, but I would suggest going to the resources section for lab 2, because this is a very maths intensive course, and a very thorough understanding of the different mathematical concepts like statistics and probability are required and must for fully understanding these concepts. Lab 3 is a comparatively lightweight lab. It deals with vectors and dimensionality reduction. So there's L1, L2 regularization, which we saw earlier in the regression notebook. And there is a very important concept known as the PCA, or the principal component analysis, which is used for dimensionality reduction. Let's dive into lab 3. So I've applied PCA on the famous iris dataset. There's a theory, again there's a code. Yeah, so we apply PCA here. Here's the covariance matrix, and here are eigenvalues, eigenvectors, and we take the first two since it corresponds to 97% of the variance, and we want to visualize it on a 2D plane. And let's plot this data out here. So this is before the PCA. If we only consider two columns at a time, so the iris dataset looks like this. And now we consider all the four columns using PCA and reduce the dimensions, and as you see, this is a much better visualization of the uh, data set. And now we can use these two for further machine learning concepts like logistic regression or SVM to classify. Lab 4 deals with again classification methods, one of which is the KNN, which is for supervised learning. In fact, all that we saw up till now was supervised learning, and K means will be our introduction to unsupervised learning, where we don't have the labels. Let's dive into lab 4. So let's first go through KNN. Again, these two are used for classification. So here's KNN, some theory part first, and then implementing our own KNN algorithm from scratch. This is as you see, using real data. This is from the UCI repository again. This is breast cancer data, and you can access it to this link here. Now in this data we need to classify a cancer if it's benign or malignant. That's for class 2 or class 4, based on uh, all these columns, all these features. So yeah, there's some data manipulation, and this is the splitting, and this is our KNN algorithm. As you can see, we can change the value of k here. For this example, I put it to be 11. You can put it to any value as you wish. And as you can see, this is the predicted list along with its confidence. For example, this data point, we predict that it's of class 4 or malignant with a 90.9% confidence. And this is our entire predictions list, and the accuracy, as you see, came out to be 96.7%. But accuracy may not be a good metric for this, so we define confusion matrix here. The confusion matrix, the theory is given here, and the F1 score, which is a very good metric in these cases, has been calculated. It's 97.5%, and so a model can be treated as very accurate. Let's head over to k-means now. So again, there's this theory. As you can see, this is unsupervised learning where we don't have the labels, and we just need to find clusters. The algorithm needs to find clusters based on the data points it has. If we give it we need to find three clusters, then it will find three. If we say that we need to find two clusters, and maybe it will go for this as one cluster and this as another cluster. But we don't have any labels, and so of course there's no wrong and right answer here. And this is a classic example of the use of k-means. The reference is Andrew Ng's course on Intro to ML, so have a look at it, it's pretty good. So this is a basic understanding of the k-means clustering algorithm, and here's the code. This is a banknote authentication problem on the UCI repository, and we removed the labels, and this is our data now, taking two columns at a time, of course. And then we apply the k-means algorithm, and after that we gave k equals to 2 first, and this is how it makes two clusters of the data that we provided it. Let's try with k equals to 3, and voila, these are the three clusters based on the data that our algorithm makes. Lab 5 covers one of the most popular and most widely used algorithms for classification as well as regression, that's CART, or classification and regression trees, also known as decision trees. So random forests are basically an improvement over decision trees, and random forests are also part of ensemble methods. Ensemble methods is basically combining different models and making a common prediction using all of those. Let's dive into lab 5. So there's this decision tree.ipynb. There's the theory. Entropy is a very useful mathematical concept, and we use it in decision trees to create such labels. So there's some description about that. There's this training set, a toy data set, and code to make our tree. And finally we have the predictions, but this is a toy data set and only one decision tree. So here we have used random forests, and the previous one was for classification, this one is for regression, and hence instead of entropy we have the standard deviation here. And this time we try it on real data. This is taken from the official Kaggle site. There is this data set on house prices. So Kaggle is an online platform for testing your machine learning algorithms and participating in competitions based on that. So now this is building a tree. We build one tree first, and this is our list of predictions, and this is our mean error. As you can see, this is pretty large, and so we need to reduce this, and we'll use random forest for this. And random forest, as I said earlier, is a collection of different decision trees, and we randomly allocate features to it. And for this particular example, we have number of trees equals to 10, and we have fitted 10 decision trees in this random forest, and the absolute error decreased substantially from about 18,000 to 8,000. So there is a 10,000 decrease in the error, and this is just 10 trees. If you increase that to 50, 100, maybe use a binary search tree instead of the one we have used, we can reduce this further. So that's that for the different labs. There's also resources section where there are the different notebooks, reference notebooks of people who have been working on this. There are different notebooks on GitHub, some references which you and I use to understand the concepts, like this one is for PCA. So I would recommend you go through these as well. And sorry about that. Along with that, there are various resources, some YouTube videos, and lectures and lecture notes, and courses, reference codes, some guideline on how to evaluate your model, like these. So these were the ones which I used to learn machine learning, and I sort of included them in this repository so that you guys can also learn from these. So that concludes our two of this repository LSPL/ML community. I would like to point out that this repository is still in the growing stage, and it will need your help as well. While learning, you may come across even more and better resources and notebooks. Please do add those as well as your exercise notebooks to the repository. For instance, we really require help for these. We need better resources for inferential statistics that we saw here. So, hope you enjoy this resource and help it grow. Thanks. This is Jay signing off.